So we looked at the idea of finding the determinant of a square matrix. The determinant is a real number that's associated with every square matrix, a very important number. And we have shown how to determine that number by what's called cofactor expansion. And we can do that cofactor expansion along any of the rows or columns of the matrix. And it's essentially, calculated by taking each row or each entry in a given row, say, multiply that entry multiply it by its cofactor and add those products up. Similarly, we can do that along any column. And we saw with a 3 by 3 matrix in general, and that requires us to compute 3 2 by 2 matrices, because each minor in a 3 by 3 matrix is a 2 by 2 matrix. Now, think about a 4 by 4 matrix. In a 4 by 4 matrix, any row or column has 4 entries, and the minor, which we use to calculate the cofactor, is going to be a 3 by 3 matrix. So when you're computing the determinant of each minor, you're going to have to do cofactor expansion again along a row or column, and that's going to require what? 3 2 by 2 matrices. So for a 4 by 4 matrix, you will have 4 3 by 3 matrices in general to compute the determinant of, and for each of those 4 3 by 3 matrices, you will have 3 2 by 2 matrices. So that's a total of how many 2 by 2 matrices? 4 times 3, right? 12. And for each 2 by 2 matrix, you've got basically a couple computations to do there, right? And what about a 5 by 5 matrix then? It's got 5 entries along any row or column, and each entry has a 4 by 4 minor. So in that case, you're going to have to compute 5 4 by 4 matrices, and for each of those 4 by 4 matrices, you're going to have to compute the determinant of, rather, those 4 by 4 matrices. And for each 4 by 4 matrix, you'll have to compute the determinant of 4 3 by 3 matrices, and for each 3 by 3 matrix, 3 2 by 2. So that's going to be what? How many 2 by 2? 5 times 4 times 3 times, right, 2 computations, basically. Do you see the pattern there? I hope you recognize that. What are we talking about? 5 times 4 times 3 times 2. If I go to 6 by 6, then what? 6 times 5 times 4 times 3 times 2. It's basically what? Going by n factorial. In other words, the determinant of n by n matrix is on the order of n factorial computations. Do you see the problem we're going to run into for very large? Imagine finding the determinant of a 100 by 100 matrix using determinant cofactor expansion. Okay. Let's look at, as you can see, it's very costly. So cofactor expansion is an important way, and we're not going to do 10 by 10 matrices by hand, but we do want to talk about how we might look at other methods for defining the determinant, and we'll do that later. But let's go on with cofactor expansion. We did this 3 by 3 example in the last video, so now let's do a 4 by 4, right? Now, if we're doing it by hand, a lot of times I can help a little bit, and hopefully this one isn't too bad. Which row or column would you want to do cofactor expansion along? Any of them? Row 1? Column 1? What would we want to do? Well, I hope that you carefully look and see that the best row or column to expand, when we say expand, we're talking about this cofactor expansion, is which? It's going to be column 3, I hope you notice, because why? There are 3 zeros in that column. Okay, somebody might have said, oh, let's do along row 4. Okay, there's 2 zeros. Okay, fine. Choose the one that has the most zeros, though. Okay, choose the one that has most zeros. That's the best way. Otherwise, you're going to do more. Certainly, you don't want to do along row 1 or column 4 or column 2, because, right, you got to compute each corresponding 3 by 3 minor. Here we only have one minor, 3 by 3 minor to compute. So if I go along column 3, the determinant of this matrix A is what? So the entry is 3. in the first entry along that third column, and it's -1 to the what? First row, third column, 1 plus 3, so that's going to be +1, times its minor. And what's its minor? If I take away the row and column that it's in, do you see the 3 by 3 matrix that's left over? That is going to be the matrix we need to find the determinant of for the minor. So that's 7, 2, 1, 3, 5, 2, 0, -1, -4. Okay, and then as I continue to cofactor expansion along this column, the next entry is a 0, the next entry is a 0, and the next entry is 0. I don't need to compute the cofactors there, right? So that's it. We're, as far as that goes. But now we do have to do this one, and so we're going to have to do cofactor expansion here. And where should we do this? Well, I would say either column 1 or row 3. I'll go along row 3. Or you could do again column 1. That would be good, because why? There's 1 0 there. You could do it along any row or column, but again, think about this smartly, right? So I've got 3, don't forget, times -1 to the 4th power, that's 1. And then I have times this cofactor, which the first entry in row 3 is 0, plus the second entry is a -1. And that, notice, is in this matrix, right? It's in the third row, second column. So it's -1 to the 3 plus 2. And its corresponding minor, you can see that, 7, 1, 3, 2. And then plus this last entry, -4. It's in the third row, third column. And its submatrix, its minor, it will be the determinant of this submatrix here, 7, 2, 3, 5. So I'm going to do this, don't forget, 3 times, I got to add all these up. So I'm getting 3 times what? That's 0. I get -1. -1 to the 5th is -1, right? So this is a -1. -1 times -1 is +1. And what's this? 7 times 2 is 14. Minus 1 times 3 is 3. Plus -4. -1 to the 3 plus 3 is -1 to the 6 is +1. So this is -4. And I got 7 times 5 is 35. Minus 2 times 3 is 6. 14 minus 3 is 11. 35 minus 6 is 29. And so I get 3 times 11, -4 plus 29. It's -4 times 30, take away 4, right? -120 take away 4 is -116. And so I get 3 times 11 plus -116 is -105. And all that wonderful arithmetic there. But there's the result, right? That's the determinant of this matrix. And so if you want to try and do cofactor expansion along any other row or column, you can, but this will be the most efficient method to do it in. Okay? All right, so how big of a matrix will I make you do? We certainly did a 4 by 4. Hopefully there's a few zeros in there to help minimize the time of the computation in showing the work. But what about a 5 by 5? Can I give you a 5 by 5? You say, as long as there's lots of zeros. Sure, I'll put some zeros in there, but I'm going to make it a little bit harder. Instead of numbers, I'm going to put letters. Ooh. Find the determinant of this matrix. You say, well, now you can't use your calculator, right? Because you can't punch in letters. But you're going to see that this is going to work out pretty good. You might recognize this type of matrix, right? What type of matrix is this? It's a square matrix. And notice that above the main diagonal, all the entries are 0. What type of matrix is this? Lower triangular. Good. If you said lower triangular, you're correct. So it's a lower triangular matrix. So let's find the determinant. What row or column am I going to expand along? You had better said row 1 or column 5 if you want to. You want the one that has 4 zeros, right? I'm going to do row 1. I'm going to do row 1. You don't want to do cofactor expansion along row 5 or column 1. Please do not do that. You'll be here all day. So what do we have? We have the first entry is A, and it's negative 1 to the 1 plus 1. I'll just do this the first time, but it's positive 1, right, for the cofactor, and then times its minor. Now its minor is a 4 by 4 matrix, right? It's 5 by 5. Take out that row and that column, and you can see the corresponding minor. So along the first, I'll have C, E, H, L. I'll have 0, F, I, M, 0, 0, J, N, 0, 0, 0, P. All right, so I've got A times 1 is A. And now what I'm going to do, again, cofactor expansion along this first row. I've got 3 zeros there. It's C, right, times its cofactor. Of course, C is in the first row, first column, so it's going to still be the same thing, negative 1 to 1 plus 1. It will still be 1 there, C times 1. And then its corresponding, right, is F, I, M, 0, J, N, N, 0, 0, P. Now I've got this 3 by 3. What am I going to do? Find the cofactor expansion, find the term by cofactor expansion along the first row. So I've got A times C times F. F is in the first row, first column entry, so it's negative 1 to the second power. 1 times what? Its minor. And that's a 0 there. You might recognize that I've alphabetically gone from A to P, but I've left out the letter O. Don't want you to be confused with the zeros and the O's. So there's no O's, but this is 0. And then I'm at 2 by 2. I don't need to do anything more, right? I know how to find the determinant of a 2 by 2. It's AD minus BC. So JP minus 0 times N. Well, 0 times anything is 0, right? And so I just get ACFJP. That is the determinant of that matrix. And it wasn't too bad. It wasn't too bad. Now, ACFJP, it's the product of these 5 entries, because these are indeed entries in the matrix. But go back to the matrix. Which entries are we talking about? ACFJP. ACFJP. Do you see? We're talking about the entries in what? The main diagonal. And now what are we doing with those 5 entries? We are multiplying them. Is that the trace? No. Trace is the sum of the main diagonal entries. But in this case, the determinant of this matrix is the product of the main diagonal entries. Is that always going to be true for any lower triangular matrix? Think about it. Think about the way we did it, right? These zeros are all going to be there above the main diagonal for any lower triangular matrix. So yes, that'll always be the case. In fact, it's not only true for lower triangular matrix, but it's also true for upper triangular matrices. And therefore, it's also, of course, valid for what? Any diagonal matrix, because it's also any diagonal matrix is upper and lower triangular. In fact, all 3 of those we call triangular matrices. So for any triangular matrix, upper, lower, or diagonal, the determinant is the product of the main diagonal entries. So by inspection, you are able now to find the determinant of any triangular matrix without doing any computation. So from now on, if I give you this one and say what's the determinant, you will simply multiply its entries together. It has to be a triangular matrix, so if it's not triangular, then this is not true. Okay, if it's not triangular, this is not true. Okay. I want to close this particular section in the book with one other method for finding the determinant for 3 by 3 matrices. It's not going to work for 4 by 4 and higher. Okay. there is a way to extend this idea to 4x4 or higher, but it's not going to work the way we show it. Sort of a neat little picture. And some of you, if you've had Calc 3 before, this is maybe the way you found the determinant. You've heard of a determinant before in the process of finding something called the cross product. And so I'm going to take a look at this so-called permutations approach to finding determinants of 3x3 matrices. Again, this method is not going to work for 4x4 or larger. And the way it works is we take products of 3 entries from the matrix. And the way these products have to be are, for any entry we take, or the three entries we multiply together, they all have to be in different rows and different columns. So for instance, I can take A11 first row first column times A22 second row second column times A33 third row third column. They're each in a different column and different row. None of them share the same row or column. So if I take all such possible combinations or permutations of this and then add those together, we get the determinant. Now, there is one thing about the permutations. Some of them are positive and some of them are negative. The best way to see how to do this, so for instance, one product is I can take A12 and then A21, right? But then I would have to take what? A33, because each one has to be in a different row or column. Okay, I can take A13, A21, and then A32, or A13, A22, A31. Now, those are the different. There's a total of 6, but here's an easy way to get them. Take our first 2 columns of our matrix and recopy them over here. Just recopy those first 2 columns over here. And now what we do is to find the determinant of this matrix A, we go, let's take one of these products here, A11, A22, A33. Okay, so going down there, I get that product. So let's write that down, A11, A22, A33. And that's a positive product, essentially in this picture, because I'm going from left to right. Another one is A12, A23, then I want to have to choose A31, right? A12, A23, A31, because they're all in different rows or columns. But notice A31's right down here, the way I've written it, so I just go straight down left to right, and I get that next one, A12, A23, A31. And then if I take A13, I could take A21, and then I'm stuck with A32, right? A13, A21, A32. But notice if I continue to go left to right, A13, A21, A32, I get them right there with that by extending that out. A13, A21, A32. And then I could take A13, A22, and then I have to take A31. Okay, but now in this sort of way of setting it up, I'm going right to left going down, and what happens there is I'm going to subtract. Those will be negative products, A13, A22, A31. And then I can take A11, A23, A32. That would be 3 different entries in different rows and columns. But notice that A11's right up here. I can just come down this way, going again right to left. And because of that, again, it's negative A11, A23, A32. And last, I can take A12, A21, and then A33. And I can get it right here, A12, A21, A33. And that's it. Those are the only combinations. There's 6 permutations is what we say, where I can take products where I get entries from different rows and different columns. But by recopying these 2, it's just a memory tool. You can get those 3 products going that way, and then the 3 products going this way. The products going left to right are positive products. Products going right to left are negative products. Add all that up, and you get the determinant. Okay. All right, so it's about, by the time you do all that, it's not much quicker than cofactor expansion for a 3x3, but it's a neat way. Now, again, it doesn't work for 4x4 or larger, so you can't draw 4x4, copy the first 3 columns, and do lines this way and this way. There's a lot more permutations that will be not seen in that sort of by doing it that way. Last thing I'll just close with is this. You can go through this, but I've equated the two methods. I've done cofactor expansion along row 1 for this arbitrary matrix. I've done cofactor expansion here. You can check and see how that works out. Find the minors, distribute, and I get these, and then if I just rearrange these, because addition is commutative, I can rearrange and I get this which is exactly what we have up here. If you compare it, lets you do that. If you want to, you can stop the video and pause it and try and figure that out. But there it is. Okay, so that's just another way. In the next set of lecture videos, we're going to look at the determinant from a different perspective, how we can, other ways that we can find it. And what we're going to look at is how row operations affect the determinant. And we're going to use row operations to help us find the determinant of a matrix. So if you were missing doing row operations, you thought we would be done with it after Gaussian elimination, Gauss-Jordan elimination, and the inversion algorithm rather, well, it's back. Yay. Or boo, I don't know. We'll do that in the next set of videos.